In this video, I'm going to illustrate how to check for certain statistical assumptions in the context of simple regression. More specifically, we're going to focus on checking for linearity between your predictor and your criterion variable, homogeneity of the variances of prediction errors or residuals, normality of residuals, and then also look a little bit look at checking for outliers and so forth. So what I have right here, I have an SPSS data file open with two variables. I have a measure of self-efficacy and a measure of achievement. And so basically I'm going to run a regression model with self-efficacy as a predictor and achievement as my criterion variable. So you could basically say that self-efficacy is my X variable and achievement is my Y variable. And so I have data on these two variables for 22 cases. So let's just really quickly, I'm just going to run a regression analysis, and I'll just go to Analyze Regression Linear and put my predictor self-efficacy into the independence box and achievement into the dependent box. And the assessment of these various assumptions using residuals plots really requires the generation of prediction errors for each case. So basically what I will do is I'll click on Save, and I have two options for residuals or prediction errors. There's the unstandardized and the standardized. So and basically the prediction errors are generated in the following way. If you can imagine, essentially the prediction equation, the regression prediction equation, states that each person's predicted score on the dependent variable or criterion variable Y is a function of a couple of components here. It is the intercept plus the regression coefficient times the person's score on X. So each person's predicted score on the dependent variable or criterion variable is a function of the product of the regression slope times the person's score on X plus the intercept. So when you are mapping out the relationship or plotting out the relationship between your variable X and your variable Y, X being the predictor and Y being the criterion variable, you'll note that you'll have a regression line, and you'll have data points that will fall around that regression line. Essentially what happens is that the regression line itself is comprised of predicted values on Y. So in other words, the regression line is fit to your data. So you can imagine that these little the plot of data points, that's the actual data that you have. So you have a plot of each person's score on X and actual score on Y. So this person right here, might have a 1 on X and a 1 on Y. This person right here might have a 1 on X and a 2 on Y, and so forth. So at any rate, the line itself is comprised of predicted scores on Y. Okay, so each person's score, when you take their actual plot of their data point and you take the difference between their actual score on Y and their predicted score on Y, which actually would fall right on the regression line, the difference between those two is referred to as a residual or a prediction error. So what we're essentially doing right here in the regression analysis, where I'm clicking on Save, is I'm asking for essentially computed residuals or prediction errors, both unstandardized and standardized. So we'll kind of map this out a little bit more in additional detail shortly. But essentially what I'm going to go ahead and do is just run the basic analysis. I'm going to click on OK, and you'll notice that when I run the analysis, you'll notice several pieces of information here. First of all, we have our R-square value, which is telling us the proportion of variation in the criterion variable, which in this case is achievement, predicted by or accounted for by self-efficacy, which is our predictor in the model. And the f-test, and this right here is just the p-value, our f-test is a test of the significance of the r-square value. So if this is statistically significant, then we would infer that within the population, the proportion of variance accounted for by the predictor variable is greater than 0. So here you see that our p-value is actually less than 0.05, which is a conventional threshold. So I would reject the null and infer that our predictor self-efficacy would explain greater than 0% of the variation in achievement within the population. And then you can see down here you've got your regression slope, oftentimes denoted with a little b. And so this is the unstandardized regression slope. Let me actually move this down here, reflecting the predictive relationship between self-efficacy and achievement. So we would interpret this to mean for every 1 unit increase on self-efficacy, there's an increase of 0.675 raw square units on achievement. If the value happened to be negative, then we would say for every 1 raw square unit increase on self-efficacy, there's a decrease of 0.675 raw square units on achievement. But that doesn't make sense, and we're going to stick with just the positive coefficient right here. So our regression prediction equation, we actually have a couple of things here. We have our slope b, and we also have the intercept. And the intercept is really nothing more than just the predicted value on y when x is equal to 0. So it would literally be this point on y. So when x is 0, this is the predicted score on y. So we can actually write out our prediction equation in the following way. So if we know that the prediction equation equals a, which is our intercept, plus b times each person's score on the predictor x, which in this case is self-efficacy, then we could actually substitute these values into this equation. And so you'd have predicted score, each person's predicted score on y is equal to 1.946 plus 0.765 times their score on self-efficacy. So I'll just say it's self-efficacy right here. So that's the basic prediction equation. So, and again, that's their line. So you have, again, the data points for each person falling at each value of x. So if this is a value of 1, you'd have a value of 2, a value of 3, and so forth. You essentially would have actual values of y that would fall around the regression line. Okay, so essentially, as I was indicating just a second ago, these are the actual coordinates for each person's case. And so the difference between a given observation on y and their corresponding predicted value, because the predicted values are what actually comprise the line right here, the difference between those two is what is referred to as prediction error. And I'll just denote that as with an E with a little subscript I. And so essentially this is computed just by taking the actual score on y and subtracting predicted y from it. Okay, so in a nutshell, as you're looking at this equation right here, we could actually, the standard equation without that would incorporate prediction error allows us to break down every piece of information associated with that person's score on y. So actually, it's a plus bx, a little subscript I here, plus that person's residual error, which is just the difference between that person's actual score and predicted score. So you could break down that person's actual score on y into these three components right here. And the prediction equation, you do not have the residual, because the line is actually what is predicted based on the model. So the thing about it is that when it comes to the prediction errors, there are certain assumptions associated with the model. And so in regression analysis, if you violate those assumptions, then what can happen is that you can run into various type 1, type 2 decision errors. So one of the assumptions is that you have homogeneity of error variances, or another term for that is homogeneity of residuals, or residual errors. The proper term for that is homoskedasticity. So, when you're looking at this regression line right here, basically what the assumption is that if I have data points that are plotted out for each value of x, or coordinates plotted out for each value of x, essentially the coordinates should fall randomly and evenly around the regression line, and not only that, but that the variances of the prediction errors should be equal across values of x. And this is really terribly drawn here, but if you can kind of pretend with me for a second, if this is my regression line, what this would mean is that the variance of the variation of the prediction errors here should equal the variation of the prediction errors here. And so this is, let's say this is a value of 1 on x, this is a value of 2 on x, this is 3 on x, 4 on x, and so forth. So essentially, what we would, if I was to take the residuals, which is just taking each person's score on y and subtracting the predicted value of y, if I computed variances for each of these, then essentially the conditional variances of the residuals, and I say conditional because there's the variances are conditional on the levels of the values of x, then essentially these variances should be equal. And this is pretty much analogous to what you see in analysis of variance when you're testing homogeneity of variances using something like Levene's test. So what you don't want to have is a situation where you see a pattern in the residuals where you see a lack of equality in those in the variances. So for instance, let's say I had another data set and I had here's my values of x again, 1, 2, 3, 4, 5, and so forth. So let's say that I had my regression line and the pattern of residuals looked more like this. So hopefully you can kind of see that there's sort of this cyclical pattern in terms of the residuals, and as scores are increasing on x, you actually see greater amounts of prediction error. So you can see that at lower values of x, you have small amounts of prediction error, but as scores on x are increasing, the variation in the prediction errors is increasing. And this is a pattern that is inconsistent with the homogeneity of variances assumption. That basically the residuals, there's inequality in the variances of the residuals across levels of x. So that's a bad sign. You do not want that situation to occur, because essentially what this is saying is that the model is doing a much better job of predicting values on y at lower values of x, but in this case it's doing a really crummy job at higher levels of x. There's a lot more prediction error. So the model, what you want is a consistent rate of prediction across values of x. And so if you happen to have a lot of inequality in your residual error variances, then essentially you've got the model is not doing the same thing across levels of your predictor. By the same token, if you had a negative, you could also have a situation where you could have high amounts of variation at lower levels and increasing accuracy at higher levels of X. So the point is that one way that you can assess this assumption is through the use of residual plots. So what we can do is after running the basic analysis and asking for those residuals, what you'll see is right here it says it's basically denoting that we have residuals that are calculated. So and in fact, I'll tell you what. Here's what we'll do. We'll rerun this, and I want to show you. I'm just going to take these out. We'll rerun the model, and we're going to ask for predicted values on Y as well. So I'm going to go to Save, and I'm going to ask for predicted values on Y. Okay, so right here you can see that we have the predicted values on Y. So this is Y hat. So there's predicted values on Y. And then so essentially we have the actual scores on Y, which is achievement. So if you take the actual scores and subtract the predicted scores, that's what gets you your residual errors. So each case in your data set has a predicted score that's based on the statistical model, and then we also have residuals. So this person right here, person 1, scored basically a negative. In other words, the residuals, the mean of the residuals is 0. So this person actually scored about 0.24 units below the mean of the residuals, which is 0. So in other words, that person's score, if I was to kind of demonstrate with the regression line, there's X, there's Y, and I was to draw out sort of the regression line, that person, at a value of 3 on self-efficacy, so let's say this is 1, 2, and 3, that person's residual would actually be below the regression line. So that person had, essentially a score of 4 on achievement and a predicted score that was actually higher. So that person's predicted score would be on the regression line. So the difference in terms of the error is actually negative. So that's why we have the negative value. The second person, you can see that their actual score on achievement was 8. Their predicted score was 5. So if you take 8 minus 5, you get the 2.99258. So in other words, that person who had a score of 4 was actually scoring above, above the predicted value. And so the error then happened to be positive instead of negative. So at any rate, we can assess the issue of homogeneity of variances by basically requesting a residual plot or residuals plot. So if we go to Analyze, Graphs, and go to Legacy Dialogues, we can go down to Scatter or Dot, click on Simple Scatter, and what we'll do is we'll plot the predictor variable on the x-axis, and we'll plot the unstandardized residual along the y-axis. And in fact, really, we'll go ahead and do this, and then I'll talk a little bit about standardized residuals. So if I click on OK, what I'm essentially looking for here is, you'll notice that, like I said, the mean of the residuals is 0. So this is the mean right here. And if you think about it, if we were plotting out our regression line again, there's X, there's Y, what is going to happen, or what should be happening, is that essentially, if you have the distribution of residual errors around the regression line, the sum of those errors will actually equal 0 at each value of x. So there's value of 1, value of 2, and so forth. So what should in theory what should be happening is that not only are the residuals randomly distributed, but they also should exhibit normal distribution. And we'll talk a little bit more about that later. But the sum of all prediction errors across values of x should equal 0. And so what you can see right here is, for this particular case right here, they're scoring above the mean on y, or excuse me, above the their actual value is greater than the predicted value. This person's actual value is less than the predicted value, and so forth. And what you're looking for is essentially sort of a random display of data points laid out right here. Okay, so what we're looking for is a lack of a pattern. So I only had 22 cases right here, so it's probably not as clean as what we would like. But basically what we would not want to see is a pattern that might look like this. Let's say I have the mean of the residuals here. What I would not want to see is at low values of x, something that looks more akin to this, where you have sort of a cyclical pattern. In this case right here, this would be indicative of non-constant variance. In other words, this would reflect a lack of homogeneity of variances, which, if this is the case, then if I was just plotting out the regression line against the data, instead of plotting out the residual plot using the actual x and y values, then what this would translate into is what I was showing you earlier regarding a lack of constant variance of the residuals. So at any rate, what we're looking for in terms of the residual plots, in terms of demonstrating homogeneity of variances, is essentially a situation where our data points exhibit random variation and no evidence of any kind of cyclical pattern around the mean of the residuals. So it actually kind of looks a little bit more like a box in terms of the way the residuals are laid out. As I said before, basically when you have smaller n's, it doesn't quite look as pretty, but this is looking fairly random overall, so there's no evidence of any kind of cyclical pattern that you can see in the data. So that would be evidence of that we would have homogeneity of variances assumption met in our data. So another assumption pertains to normality of the residuals. So in other words, what this means is that the residuals ought to be normally distributed at each level of your predictor variables. So in other words, you should see normal distributions. And so going back and just plotting x versus y, what this would effectively translate into is that if we have our prediction errors around our regression line, then what this would also mean is that the residuals ought to be normally distributed around those regression lines. And so if you think about it, then the positive and negative residuals ought to cancel out, meaning then that the sum of the residuals, and also by extension the mean of the residuals at each value of x would be 0. So these are not really well drawn normal distributions, but if you can kind of imagine those distributions kind of overlaying with the residuals, so you have effectively the assumption that the variances for each of these conditional distributions for residuals, the variances are equal across values of x, and then also the residuals at each level of x are normally distributed. So one way to assess the normality assumption is to essentially test the normality of the residuals using some standard techniques that you would assess normality for any variable. So if we go, just kind of going back to the data set, what I can do is I can go to Analyze, Descriptive Statistics, and go to Explore, and I can put the unstandardized residuals into the dependent box. Statistics are already there, a number of defaults are already listed. If I want to check for possible outliers, I can certainly click on that as well. Under plots, I can click on histogram, and I can click on normal probability plots and continue, and I end up with a number of pieces of information here. So you can see that first of all, you got skewness and kurtosis statistics. When you're assessing normality, skewness and kurtosis are two aspects of normality. So it's theoretically possible to have zero skew, but still the data is not distributed normally because you have positive or negative or kurtosis. So in effect, when you're looking at these values, just think about each of them as having kind of their own scale, where 0 would reflect no skew if I'm looking at the skewness dimension. A positive value would reflect positive skew, and a negative value would reflect negative skew. So, a positively skewed distribution would look like, something like this. A negatively skewed distribution would have a little bit more of a distributional shape that looks a little bit more like this. So this is a positive skew, and this would be a negative skew. And so in terms of kurtosis, you can also imagine the same sort of dimensions here, where the 0 is a mesokurtic distribution, which in terms of kurtosis would be consistent with a normal distribution. A positive value would signify that you have a leptokurtic distribution, and a negative value would signify that you have a platykurtic distribution. So the thing about it is that when you're assessing these kind of more descriptive indices, you have to keep in mind that really your data will never perfectly match a normal distribution. And so what we have to do is kind of develop some tolerances for what constitutes good enough or close enough to that we can say for all practical purposes that our inferences are not going to be unduly impacted by the departure from normality. So in terms of assessing skew and kurtosis, there are various rules of thumb on these. One of them is just to say, well, if you have a skewness value that is greater than +1 or less than -1, then you have a more substantial skew in your data. And the same would also go in terms of interpreting kurtosis. Kurtosis is even a little bit fuzzier. There are other rules of thumb there that suggest much more extreme values for representing extreme departures from normality on that dimension. But looking at just this, using this sort of rule of thumb right here, you can see that both the skewness and kurtosis values were fairly close to 0, which would suggest that we don't have a situation where there's extreme skew or kurtosis in terms of our residuals. So when we scroll down a little bit more, you can see also you have tests of normality. You've got the Shapiro-Wilk and the Kolmogorov-Smirnov tests. And so these are p-values associated with those tests right here. And so these are tests of departures from normality. So if the p-value that is printed is indicating a significant departure is, say, less than 0.05, less than or equal to 0.05, this is just again a conventional rule of thumb, then you would infer that your residuals are departing significantly from normal, which is so typically when you're testing hypotheses. You generally want P to be less than or equal to the alpha level, let's say 0.05, and that's actually a good thing. When you're testing statistical assumptions like normality or homogeneity of variances and things like that, you don't want that to be the case. So in this case right here, for both of these tests, you can see that the p-value was greater than 0.05. Because of that, we would essentially conclude that the data seems to fit a normal distribution. So it appears to be that our residuals are fitting a normal distribution. Okay. Now another way in which you can assess normality is just visually using a histogram. So here you can see a histogram. You can see that really there's not a strong, overall it looks like it looks fairly symmetric, and there's not really a strong indication of a departure from normality visually. So you have a little bit more evidence that our residuals are fitting a normal distribution. Other kinds of plots, you have the QQ plot. And so what you're doing is you're looking to see how closely your observed values on your predictor variable, how closely they are fitting this regression line. And the regression line is reflecting what would be expected if the data were following a normal distribution. So as long as the data points are kind of falling, very close to the line, that would signify that you've got evidence of normality. What you don't want to have is a situation where you'd have the plot of this regression line, and you'd have like some substantial departures, and it would kind of look like this, so you don't want to have really substantial departures from normality. That would be a pretty problematic distribution of residuals. So at any rate, our current data set does not seem to suggest that. You also have a box plot of the residuals, and in terms of interpreting the box plot, these edges right here, this represents the 75th and the 25th percentiles on the residuals. So essentially, it represents the middle 50% of the distribution. You have this line right here, which is actually representing the median residual for the residual variable. So you can see that really, and the whiskers are capturing the upper 25% of the distribution of residuals, and the lower 25%. So as you can see, the residuals look fairly symmetric. In terms of the amount or the distance between the residual points for the 75th percentile and the median right here. There's a little bit of a difference here. You've got a little bit greater difference here between these points than these points. But overall, it looks like there's pretty good evidence that you have symmetry in your residuals. So the long and short of it is, and by the way, so in the plot though, so every once in a while you might have a plot, you might have something like this where SPSS might give you a little data point. It might have like 110 or something like another plot where it was 99 or something like that. This is one way in which you can assess for outliers. So essentially, this would point to case 110 in your data set or case 99 in your data set that are potential outliers. So that actually brings up another point, which is the assessment of outliers. You know, when you're looking at you can actually look at the residual plot, and you know, there's no real evidence of outliers, but sometimes what can happen is that when you're looking at your residual plot, you know, you might have something that looks a little bit more like this, where you have, you know, you might have, you know, your data points randomly distributed around the mean of 0 for the residuals. But then let's say, for instance, you have a case that, you know, might look like, you know, this right here, where you got a data point that seems to be departing from everything else, or, you know, you might have another data point way out here or something like that. So the point behind this is that this data point then becomes a little suspect, and maybe what this is signifying is that you have a bivariate outlier in your data. With a bivariate outlier, this is a little different conceptually from a univariate outlier. With a bivariate outlier, what happens is that, you know, if I'm going to just kind of lay out an example here where I've got my regression line. Oops. No, that's not going to work. Let's say my data points roughly kind of demonstrate this pattern, where it looks like overall there's an increasing trend in terms of the relationship between x and y. Okay, so if the data kind of demonstrates this trend right here, you know, if I was creating a regression line through this, you know, it would signify that we have a pretty good relationship. But if let's say I had one data point that fell way out here. In this case, what it would do is it would actually drag the regression line down, and the regression line, when it was computed, would look more like this, which would be more consistent with the suggestion then that the regression coefficient, or the regression would signal a lack of predictive relationship between the two variables, all because of the presence of this outlier right here. So this is what is called a bivariate outlier. It doesn't necessarily have to, you know, if I was to kind of imagine a normal distribution on x and a normal distribution on y, it doesn't necessarily have to be a univariate outlier in order to be a bivariate outlier. What can happen is that if I have a data point that departs substantially from the remaining data points, or the plot of data points, that would be our bivariate outlier. And so the effect can be to you know, decrease the magnitude of the regression coefficient, and essentially suggest a lack of relationship, when in fact without that outlier maybe there would be a relationship. On the other hand, you could have a situation where there is essentially no relationship between the two variables, but the presence of an outlier. So in this case right here, the regression line would be you know, the slope would be equal to 0. But if I had an outlier, let's say up here, then what would happen is it would actually pull the regression line in that direction, and it can actually suggest a relationship that would not be there otherwise. So if this is x and this is y, pretend like this is just a straight line right here. It would pull the regression line, and it would give the impression that the relationship is actually greater than 0. So the outlier can have some pretty profound effects on your interpretation of the relationship between your x and y variables. So that it's very important that you assess for the presence of outliers. So one way that you can do this is you know, looking at the residual plots and seeing if there are any cases or observations that really depart substantially from the remaining observations. So, like, imagine I have a you know, an outlier, a residual that's way up here. You know, that seems to be clearly a departure from the pattern that you have elsewhere in the data set. So so that might be a candidate for being an outlying case. Additionally, you know, if we go back and we look at residual statistics and so forth, let me see if I can find our test of normality and so forth, you'll notice that we have extreme values, and it actually gives you candidates for being outlying cases. So you can see that you've got the highest and lowest unstandardized residuals, and so these cases right here in your data set might be candidates for possible bivariate outliers. The downside of this is that when you're looking at the residuals, it's all right now everything is unstandardized. So it's actually dependent on the original scale of your variable, and this is where asking for the standardized residuals is really handy. So the standardized residual is just basically taking the actual unstandardized residuals and dividing it by the standard deviation of those residuals. And so in a nutshell, these residuals are converted to z-scores. Okay, so essentially then the way this sort of works is that what you do is, or what you can do, one way of assessing for outliers is to basically look for z values that are either less than 2 or excuse me, less than -2 or greater than 2. So as you're looking at the data set right here, you'll notice that none of the z values actually meet either of those two criteria. So that would actually suggest that there's not really any kind of strong presence of any kind of outliers in the data. So let's say, for instance, I had another case down here and I had a z value for residual equal to 2.03. In that case right there, that observation would be a candidate for an outlier. So the thing about this is that when you're going back and looking at going back and looking at our output, and when we were assessing normality, you'll notice that one of the things that we've gotten was let's see here, this extreme values. And the thing to note about this is that these are candidates for possible outliers. This does not necessarily mean that these cases are the actual outliers. But and remember that basically the values that are presented are essentially, they're essentially the unstandardized residuals. So like I said, these are scale dependent, and so these are not particularly handy. So if one of those extreme values that we saw was pertaining to case 4, and so in terms of the residual, it was 3.227. But when we compute the standardized residual, you can see that it's actually 1.77. So even though it could theoretically, relative to all the other cases, it's one of the larger residuals, it's still not. There's not really any evidence that what we have is a true outlier when we look at the standardized residual. So at any rate, there's also another type of residual that you could ask for, which is called the studentized residual. So if we clicked on studentized, studentized residual is actually a little bit more sensitive when it comes to detecting outliers than the unstandardized. So this is from the first run right here, and where we had the predicted values, residuals, unstandardized and standardized residuals. This is just a replay of those first 3 columns that I showed you over here. And then these are studentized residuals. And so these are a little bit more sensitive when it comes to then trying to use that greater than 2 or less than -2 criteria. You can also assess, look for outliers visually with the residuals plot using the standardized or the studentized residuals. So if we go to graphs, and run the scatter plot again. I'm just going to go ahead and ask for the standardized residuals and then click on OK. You'll notice that the basic shape is the same as what we had with the unstandardized residuals, but you can see visually too, that here's the 2 and down here's the -2, and so what you would be looking for in terms of assessing for outliers are observations that fall below the -2 or above the 2 when it comes to the standardized residuals. So, in a nutshell, you can use the scatter plot to sort of look for visually look for outlying cases. So at any rate, that's my discussion of normality assumption, homogeneity, variance assumption, and a look at outliers. There's one other assumption I want to briefly mention, which is the assumption of linearity. And with linearity, basically the idea is that the relationship between your predictor variable x and your y variable is a straight line. So in other words, the data has to be, when you fit the regression line to the data, then it basically has to, a straight line has to best fit that data. You don't want a situation where you have something like this, where your data for the relationship between x and y, it looks like this. So here's an example where you have what's called a quadratic trend. So with a quadratic trend, you have basically a bowl shape in your data. So if I try to fit the regression line using linear regression and not using any kind of higher order polynomial regression, what will happen is that the regression line will then be flat, and the slope will be close to or equal to 0. Now, the problem with this is that when the slope is 0, the assumption generally is going to be that if I fit the regression line to the data points are randomly distributed around the slope. So if this is x, or around the regression line, so if this is x and this is y, then what you would have is essentially your data points or coordinates would fall around the regression line in this kind of way, meaning that as scores increase on x, there's no systematic tendency to increase or decrease scores on y. So in other words, this would signify an absence of relationship, so a slope of 0 is actually meaningful in that context. Now, if the data actually follows a trend such as this, then a slope that's equal to 0 is being interpreted to mean this, which is that there's no relationship between x and y, when in fact there is a relationship between x and y. It's just that it is a nonlinear relationship. So that is a big problem, and that's something that you want to be sure to check out in your data, whether the data points seem to be following a linear or nonlinear trend. And you can easily, there are a couple of ways that you can detect a nonlinear trend in your data. One is that if you plot out your residuals against your values on your predictor, one way of detecting a nonlinear trend is if you happen to have, here's the the mean predictor, the mean of the residuals. If you happen to have, it's a plot that sort of does this number, where essentially you can see that there's a curvilinear trend or some other nonlinear trend. What you want in a residuals plot is random distribution and no pattern emerging in terms of the residuals. So in other words, the residuals themselves, when we are looking at the residuals versus values on x, what we want is a random display of residuals around the mean of the residuals. So if you happen to have any kind of trend that looks like this, or some other nonlinear trend in terms of the residuals, that would be evidence of nonlinearity between your predictor variable and your criterion variable. So there's E and there's the X there. There are other ways as well that we could assess the linearity assumption. You can easily, if you go to graphs and just run a scatter plot, then in this case, I'm just going to leave this as, actually I'm going to take this out and just put my original dependent variable or criterion variable in, click on OK, and just kind of getting a visual of the data. This is what it looks like. So you can see just visually that scores are increasing on self-efficacy, scores are increasing on achievement. Lower scores on self-efficacy are associated with lower scores on achievement. And I can actually, if I double click on this and go up to add fit line at total, it actually gives me several options in terms of looking at linear and nonlinear trends and seeing if the data seems to match any of those trends. So you can see a straight line really fits this data very nicely. If I ask for a quadratic trend or a cubic trend, essentially what happens is that in this case you can see that there's like a shade of a bend here, an effort, but it doesn't really seem to fit the linear the data very well. It looks like that by adding a bit of a bend to it, it still is not departing substantially from what you would expect with a linear trend. Or a cubic trend, if you click on apply, that's kind of the shape there, and it doesn't seem to really follow the data very well. So visually, the linear trend seems to do the best job in terms of fitting the data. In addition, another option is if you go under Analyze, Regression, and then go down to Curve Estimation, what you can do is you can put your predictor variable down here, your dependent here, and you can ask for various trends to be tested out. So these are various polynomial regression models. You've got essentially a linear trend that's being compared, that you can compare against a quadratic or cubic or any other type of trend. I'm just going to go quadratic as a higher level trend. Click on OK. And essentially what you're looking for, you're looking for significance related to the different trends, and you can see the R-squared values. It actually turns out that the linear and quadratic trends have similar R-squared values, and both of them were statistically significant. So there might be a flavor of a bit of a quadratic trend in the data, but it's not really great. And a lot of times what you'll see is that when you're comparing the trends, there's a little bit more substantial difference in terms of the significance levels and the R-squared values than what you have right here. So all things being equal and adopting the more parsimonious model, even though the models seem to be fitting roughly equally, the more parsimonious solution would be, I would say, would be a linear trend as opposed to a quadratic, even though the quadratic might explain just a hair more variance in the dependent variable. It's not enough that I would be willing to go with a more complex model with the quadratic equation. So at any rate, that just kind of gives you a rough overview of some strategies for looking at assumptions with respect to simple regression. There's another assumption which is called independence, and there are various strategies to look at violations of that assumption. You can have violations of independence that might produce violations of homogeneity of variances and things like that. So I'm not really going to go into that in this particular video, but I wanted to let you know that there is that assumption as well. The basic idea with independence assumption is that the residuals are randomly and independently distributed, and and as you can see with our residuals plot visually, the residuals seem to be distributed randomly and independently. So I would also say then that assumption appears to be met with our data here as well. So that pretty well concludes this discussion, and I hope you find this video helpful.